I mentioned last time, apply principles of conservation of energy. So we have this 10 kilogram block up at the top. It's released from point A in figure 855. Track is frictionless. This part is frictionless, except for the portion between B and C, which has length of 6 meters. The block travels down the track, hits a spring of force constant, 2,250 newtons per meter. And compresses the spring 0.3 meters. So as soon as it hits, it compresses it. At that moment, all of that kinetic energy and the work done by friction gets converted into this spring energy. So it momentarily stops. So again, a method you can choose. You can put your own personality into it, of course. Obviously, you will. Draw the picture, write down the given information, read and reread it. The question, because it's very important that you visualize, you capture everything that's happening in this system from beginning to end. The context is conservation of energy. So we have to be aware of what we're choosing as our beginning stage and our final stage. Could be here, A to B, A to C, A to D, if you will. It doesn't matter. But whatever 2 points you choose, find the energy at those points. From A to B, we have potential to kinetic. A to C, we have potential, we have kinetic, and we have work done by friction. A to D, we have everything. We have potential, kinetic, friction, spring. But something about the kinetic energy is a little peculiar. What do you think it is? How much kinetic energy is there at the beginning?
None.
You're afraid to speak up. Okay, fine, you can choose to do this. We have 0 kinetic energy, it's not moving. Kinetic energy is a function of speed, therefore there's none at A. Don't be squeamish about it. We just have to make sure we have our definitions down. Kinetic energy is a function of velocity. Potential energy is a function of height. It has a height, it's not moving. All the energy at A is potential, gravitational potential, because the force only there is the force due to gravity. We're going to imagine this whole thing's closed off to the environment, closed off to any type of nuclear power plant that's down the road. So we're only focusing here. So we also have the work done by friction here. If this was nice and smooth, hey, we got A to D, life's easy. Well, got that pesky friction right there. So without friction, we have this situation. This goes back to your notes, or it goes back to the first principles, the ideal situation when there's no friction or air resistance. The energy is saved. The sum of the changes in all types of energy is equal to 0. That means it's constant. There is no change. No, the changes equal 0, aka no change. This is without friction. You're looking at this problem and you're thinking 2 scenarios. Conservation of energy or not. Pick one that works for this, which is no conservation. Set things equal to each other, find what's given. But that's all these physics problems have an overarching theme. No matter the shape of the ramp and the path and the distance and what is this and going on, you have a couple of principles at all times, minimum or max, to deal with. And it's best to reread the question, calm down, write what's given, think about what's happening. Look back at some previous examples that may be similar. If not, come back. What can you do first? What can you identify? Just start anywhere. All right. The non-conservation case, which is what we have here. Friction, the work done by friction, which is friction force times displacement, equals all of this. And we know it's always going to be energy taken out of the system. You know, so it's negative. The object starts from rest and it ends at rest when it hits here. So the change in kinetic energy would be
0.
Exactly right. The initial velocity and the final velocity are the same. 0 minus 0, 0, the whole term dies. If there was no spring there, it hits the wall, then we'd have a final kinetic energy. The spring converts, or the energy that's coming into that spring is converted into spring energy. You're always dealing with conservation of energy problems between 2 points, and there's conversions of all types. Spring becoming potential gravitational potential energy, becoming spring potential energy. There's a little bit of friction there that gets lost, so it's not exactly the same as it was. But this is our scenario. We don't have this because we have friction. We have this, and so therefore we can start to attack. Determine the coefficient of kinetic friction between the block and the rough surface between B and C. Mu K is the object. That's the goal. That's the king you're trying to get to for the checkmate. Make sure you identify everything else. Do we have any other variables that are unknown? If there are, we must get that first, because the ultimate goal is to checkmate that. Looking at the problem as is, we don't have any other unknowns. We just have that one. So the rook has a clear path on the left-hand side of the king. There's no queen on the board. We have a knight out of position. And we have a bishop that's going to be diagonal from the king. Rook comes down, checkmate. Okay, so let's now get what we're trying to get. We know that, so this guy is going to be on a flat surface. So he's cruising along. So the normal force is the weight. There's no angles of any kind. So life's easy. You can get this now. We have okay, let's, and this is where those pesky variable expressions, we're gonna get the variable expressions because that tells us everything we need to know, like in language. Math is the language of physics, a language. It's definitely a language, the overarching language. It's totally not applied mathematics. You apply math, but it's not applied math. Okay. So now we put all our numbers in here so that we have our expression from UK. It's going to be mg delta y plus 1/2 k delta x squared over 2. Or over 2, and then we have our mg delta x there. Okay, now when you put your numbers in here, it's going to be mass of 10, 9.8 times 3, times 0.5, which is half, 2250. The displacement of the spring, put that all over the mass of the block.
Mr. Kelly, shouldn't we put the spring force, spring energy as negative, as opposing energy?
Yeah, that would be actually yeah, negative. Yeah, because friction, yeah, the whole thing's going to be negative because friction is taking energy out of the system. And the only reason why we're going to make that, well, the one reason why we make that substitution, so let me rewrite this. So this actually should, the whole thing should be negative, actually. So this is going to be negative, and that will be negative as well. So yeah. And then let's this will be 0.3, this is going to be 6. And the reason why that's 6 is because that's the displacement over which the block went over the friction surface, 6 meters. So putting everything, solving that out, we should get roughly 0.328. And your coefficient of kinetic friction and static friction will always be less than 1. So that's your setup. And that is the final solution. Any questions on that? That's what you should have got for 55. Okay, I'd like to try number 21. If there are no questions on the previous one, we should get that as the final answer. Okay, flipping back a couple of pages to number 21. We have a ramp situation. $30 there. Problem we didn't have for homework, but a nice practice problem. $5-kilogram block, set in motion up an inclined plane with an initial speed of 8 meters per second, comes to rest sometime later. It comes to rest after traveling 3 meters along the plane, which is inclined at an angle of 30 degrees to the horizontal. For this motion, determine the change in the block's kinetic energy, potential energy of the block Earth system, and the friction force applied. So we have our block here. It travels 3 meters. Let's see, this is 3 like so. First thing is we got to find the change in kinetic energy. What could we do for that? Yes, the work is equal to the change in kinetic energy. Exactly. And we have another question. Well, his final speed is 0, but his initial speed is 8. So we can still use it because what's going on is that the work, the implication here is going to be friction. What would you say, the net work in this case? Yeah, one equation. So net work is delta KE, which is 1/2 mv final squared minus vi squared. So again, this question here is directly on principle. Change in kinetic energy is equal to, what do you know it to be equal to? You can go rifle through your nose, rifle through the book. Change in kinetic energy is equal to work. It was also equal to net force times displacement. Am I presented with a net force first? I am not. I could find it, but why do all that? Because it's going to be redundant. We're going to be going around to come back to where we should have started from anyway. Change kinetic energy, 1/2 mv final squared. And we have enough to find the delta KE. So no need to go around, jump around, right? So getting there, Sin. Okay, so don't quote a line in Glengarry Glen Ross, Al Pacino. Don't open your mouth unless you know what the shot is. I'm not saying that to you, but the implication is it's coming. All right, so 1/2 of the mass, which is 5, 2.5, 0 minus 8 squared, that becomes negative 160. Because you got it, and that's great, but I don't think we all we're here yet. And I want everybody to be here. I want everybody to be on the same boat. The questions on that. Change in kinetic energy is, no, I know. I'm just joking. It's a wicked joke, but it's a joke. Okay. What's part B? The change in the potential energy of the block Earth system. Julius, what's my equation for potential energy? I want Julius to. Thanks, Nicole. It is MGH. So the change in potential energy is going to be mg delta H or delta Y because it's a height. So I want to get the change. Therefore, let's look back at the ramp because, so we can go back here. Okay. Now here is the deal. You might say to yourself, how is there a height? I mean, we know we have this distance of 3 meters, angle 30, we got all this other stuff. Well, not only is it going to go up diagonally, but it actually also climbs up vertically. Remember, it's like that ramp. The path on how to traverse this distance is not important. Everything in physics is about the linear path or the displacement between 2 points in a linear fashion. Even though it goes up this path here, it still is going to go from this position, which is, we're going to define this as our reference point. We can go down here or here or here, anywhere, but in terms of where the block is in the picture, our starting point will be where the block is. We can define 0 to be anywhere. That's something we've been doing from the beginning. So HI is equal to 0 here. And then it's going to go up to this final position, which we're trying to find. It is going to climb from initial to final. So the displacement is final minus initial. Who cares how we got there? Because this is still that point, and this is still that point in vertical distance. Do you all see that? It's all about the vertical distance. Height, remember, y-axis, h, delta y. So we know what HI is. We need to get H final. How will we get H final? What do we have here? What kind of figure is this? It is a right triangle, and yes, 3 sine 30. But, let's answer the first question first. Yeah, sure. But good, I'm glad that hopefully, apply that to all things similar, but this is a right triangle. So we can use a little trig here. This is still 30. I have 30s all the way through. Similar triangles, implicit geometry application. So delta PE is going to be mgh final minus h initial. We have to get the h final. So this is our ultimate goal. This is the king. We got to get this guy over here. So HF, as Nicole told us, is 3 sine of 30. Why is that? Because this is the opposite leg of this angle, and that opposite leg corresponds to the height change. 3 sine 30. All right, so let's go ahead and get our final answer. Change in gravitational potential energy is going to be 5 times 9.8. This is 1.5, 1.5 minus 0, 1.5. And that gives me 73.5 joules. So I've increased my potential energy, gravitational potential energy. That's what we were, we stipulated way in the beginning when we were talking about these terms. When I raise the ball or raise the object into the air, as is what's going on here, I'm gaining potential energy. If the block was coming down, I'm going to lose potential energy and gain kinetic. So the more I get up here, I'm losing kinetic energy and gaining potential until I reach a final height. At this point, when I'm stopped, then all the energy is potential and none is kinetic. Okay, so that is letter B. Letter C, what do we do? What is the friction force exerted on the block, assumed to be constant? How would we approach that? We want to get the friction force, not the work done by friction. We can probably use that, I don't know. We want to get the friction force. Is there something that we can do before we get the friction force? What's going on in the problem? What can we extrapolate from it to get?
Is it the lost energy?
Okay, how do we do that?
Kinetic minus potential.
Yeah, essentially it's going to be a subtraction. We can say potential minus kinetic, whatever the case may be. What Sin is invoking is correct. Maybe, maybe not. I'm not going to hypothesize on how he's thought about that. But anyway, what we can see here is that we're losing energy. The implication that there's some sort of friction, because friction is always going to take energy away from the system. We're coming to rest, we're slowing down. So it's what else could cause us to slow down besides air resistance? Friction. So there is friction, and though they didn't say, oh, the coefficient, this is a rough surface, we know that principally because we can go back in our section in our book and understand that every time we have a negative term for energy, negative number here, friction is involved. We have slowed the object down and the energy is negative. We've lost that amount. It's gone into the environment. It's, when you rub your hands together, your hands get hot because the kinetic energy of your hands is now converted partially into the heating up of your hands. That's the loss of energy in that motion of your hands. Same thing here, a very similar concept. Problems are going to be their own episodes, but the principles remain the same. You have to always be aware of the principles. Okay, so there's friction. And so what Sin has told us is accurate. Work done by friction. There is no conservation of energy. We've lost it. It's going to be equal to change in kinetic plus change in potential. And then we have both of those from B and C, or A and B. And change in kinetic energy is minus 160 plus the potential up there, 73.5, equals the work done by friction. Then the work done by friction will help us get the force of friction because the work done by friction is equal to the force of friction times the displacement over which the blocks move. we have to get those, keep those parallels going. The energy lost to friction is this, but the work is, or the loss in kinetic energy is this. And the work done by friction is going to be the sum total because friction is going to be taking every form of energy out. You got kinetic, I'm taking it away. Potential, taking you away. Kinetic and potential, I'm taking you away. Kinetic and potential and spring potential, taking everything out. It's my job to do that. It's friction's job to take until that thing comes to rest. You've lost all of the energy that was once here. Put your foot on the brakes. Friction, 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 friction. You come to rest. The principles are very important. This is why I stress and give you the abstract problems, because I want you to extrapolate the behind the scenes nature of everything that's going on, where the numbers become, you know, icing on the cake, trivial. Because here is the magic. Here is the solution. These, okay, it's fine, numbers. This, you only get here from here. Negative 86.5 joules of work done by friction lost, which is the sum of the lost kinetic energy and the potential. So then the work done by friction, which is friction force times displacement. Force of friction is this over this. What is that, 3? And that's roughly negative 28.8 newtons. And then letter D, we want to get the coefficient of kinetic friction. Now, UK mg equals force of friction. Now, this would be good, but what's the problem? Or can we use it? It is a slope. So we have, it's on a ramp. So we can't say just mg, because mg is going to be pointing down. Okay, that's always going to be pointing down. We're not going to be concerned on the numbers. We want the principles first. Let's not worry about the numbers. Let's diagram the principles. I'm not concerned with the final answer. Okay, so what Nicole's saying basically is we need to do a little making sure, can we use this or not? And then we have to use like a little free body diagram here. Sin and Nicole all over it. Okay, let's see. That's why being careful is important. Okay, make sure that you can categorize everything, and there's nothing arbitrary in the process of the solution in physics. You arbitrary the hypothesis and all that, but it's very careful in considering everything. So you have to re-diagram it, think about it, you know. Okay, normal force, weight, mg here. Okay, and Fn is not going to be mg, it's going to be mg cos. Look at this problem. It involved energy, obviously, friction, free body diagrams. It's starting to build. You can do things like, oh, how much time did it take to get up there? What's the acceleration? Got the displacement. What's the change in the momentum? You can start putting a lot of things together once you practice. So we're not going to use mg, is going to mg cosine theta equals the force of friction, which we got is 28.8. Then we can find out our mu k. Let's see, it's 5 cosine of 30. And blah, blah, blah. This becomes 42.4. You're going to get 0.6 7.9. And that's, I want to do this problem because it involves this ramp. And I think the crucial factor there is recognizing that there is gravitational potential. There was another nice problem in the other book that involves like all the aspects. I thought they would put it here. It's the same authors, but they didn't. Any questions on any parts? I took out 37 because it involves some triple acceleration, but hey, if you want to, power through and do that, so that's out. Yeah, so okay. MG sine, it would be cosine because of the free body diagram here. Normal force, MG cos. Oh, it should be negative. I trivially left the sign out. No worries. And as we can see, this is going to be -2, so it's going to be coming out to be positive. Yeah, so no worries on that. I'll be careful not to be loose on the signs. Because this is, pointing down, and generally our motion, if motion's going up, I like everything being positive, my acceleration being that direction, and my deceleration being the same rate coming back down. So this is why this is going to be negative, and friction will be negative, which is what we got up top. Yeah. I like that number 65. Nice playful problem there. So the other book is number 88. Let's do a power question because let's do number 28. Oh boy, come on. So electric motor of a model train, remember power is work divided by time. Electric motor of a model train accelerates the train from rest to 0.620 meters per second. Oops. In 21 milliseconds. So we got seconds here, milliseconds. We got to, convert to seconds. Let's do that. The total mass of the train is 875 grams. So convert that to kilograms because that's the standard. Find the average power delivered to the train during the acceleration. Why don't you guys take a few minutes to do that? We got, we'll stay here. And just chime in when you have the answer. And back to you, Joya. No, I don't want to be dismissive or anything, but you can have negative numbers, obviously, because if your friction, that's always negative, and the work is always going to be negative. The work done by friction will be negative. Friction negative, because friction is always work done by friction always takes something out. So yes. I think you were asking in terms of the mu k, maybe. If that was the case, your mu k can never be negative. It's always a constant positive number, like percentage. So how do we do that? So now we have a couple of options. You know, remember power, work over time, could be this, could be this. We don't have a height, so we probably won't use this one. Force times constant speed. We don't have a force. We certainly could get there, but you know, is there something easier? I think something's easier. What do you think, Emmanuel? What do you think you can do here? Which one would be the easiest equation? Got any ideas? I'm sorry, I didn't hear you.
I'm not sure. I'm not sure which one to use. I'm still kind of thinking.
Yeah, sure. No problem. Hey, that looks pretty good. Both Sin and Nicole are right on the money. Yeah, let's use this one. We have the change in velocities here, and we have the time. Yes, it is. That would be too much work. So again, but there's an option. So if you want to just like be a sadist, or you know, kind of knock yourself out, you could find force and make sure that it equals everything. But we don't have time to play around half the time. So let's do change in kinetic energy. So let's convert that mass to kilograms. It's 0.875 kg. So let's do mv squared over 2 delta t, which will be 2.1 times 10 to the minus 4. I think is that accurate? Minus 4 seconds. And we got the V change, mass. Yeah. So that's what we'll do. It's most efficient. So you got final speed 0.620, 0.62 squared minus 0.62 squared minus 0.62 squared over that. Yeah, let's see. You mean the conversion or your final answer? I sometimes get that. No, because it's going to be 21 times 10 to the minus 3, and then we move the decimal over one more as 10 to the minus 4. Right? Is that 2 to the minus 2?
Yeah, wouldn't it be 10 to the minus 2 because you already moved the decimal 1? So
okay,
you
I know. I'm just saying. I get that. It's like I don't even know how to subtract anymore. It's just 10 to the minus 2. Then okay, 10 to the minus 2. Because if it's going to be a positive number, then we add one more. We add, so it's going to be minus 3 plus 1 minus 2. All right then. I knew something was off. Okay, so I mean. All right, so now let's calculate that. What do we get for, I mean, and the answer will be in watts. Let's see. We can calculate that. Yeah, perfect. Yeah. So that's 8.01 watts, joules per second. That's how much power is used by the motor. So again, we have a few options. Does everybody see why we use change in kinetic energy over time? Don't just write this down and forget about it. We must ingrain this basic understanding before it gets weird. Power is work over time. Work is change in kinetic energy. Work is also equal to change in potential energy per time. And it's also equal to force times velocity because work is also force times displacement. So if you will, you can have even another equation in there that equals this, equals that, equals this. And this here is just the original equation. My pointer not there. So all right, so that's about it. We have 1 more minute. So turn that guy in, and tomorrow we'll be doing maybe a couple more of these and go into momentum.
Mr. Kelly?
Yeah.
Why did you multiply time by 2?
Because 1/2 mv squared, and the 2 goes on the denominator.
Oh, okay, got it.
Yeah. Okay, guys, thank you very much. See you later.